Chapter 5 Helmholtz Energy and Gibbs Energy. Section 5.7 Changes of H and G in chemical reactions. In a chemical reaction, the enthalpy of the system changes, even if the temperature and pressure remain constant. This is just because the initial state of the reaction system is different from the final state of the reaction system. In the initial state, we have reactants. In the final state, we have products. They're just different, even if they are at the same temperature and same pressure. In this case, we have the standard enthalpy of reaction is equal to the standard enthalpy of formation of products minus the standard enthalpy of formation of reactants. What about the standard internal energy of reaction? U and H differ by PV. So delta U is delta H minus delta PV. Now let's look at the standard Gibbs energy of reaction. It is equal to the standard Gibbs energy of formation of products minus the standard Gibbs energy of formation of reactants. And what about delta A, the Helmholtz change? Well, since A is G minus PV, and therefore delta A is delta G minus delta PV. At a given temperature T, we have delta G is equal to delta H minus T delta S. This is just because G is defined to be H minus Ts. So delta G is delta H minus delta Ts. And when T is constant, delta Ts is T delta S. We have this equation. The Gibbs energy of formation of pure elements in their standard state at the room temperature are chosen to be zero references. For example, if you have pure oxygen gas with 1 bar pressure, its Gibbs energy of formation is 0 at room temperature. Meanwhile, its standard enthalpy of formation is also 0. And based on these two values of 0, we can say, well, the standard entropy of formation of the oxygen gas is also 0 at room temperature. And note that the standard entropy of formation of oxygen is different from the absolute value of the molar entropy of oxygen with 1 bar pressure. The former is relative to pure elements at room temperature. The latter is relative to 0 Kelvin oxygen crystal. So major differences. Alright, over here we use the 0 reference at room temperature, and the oxygen as the 0 reference should be in the gas phase. Over here we use a different reference at 0 K, and that 0 reference should be oxygen crystal, a perfect crystal of oxygen. Alright, but either way, if you just keep using the same reference, same set of references in your calculation, you will always get the same entropy of reaction. The enthalpy of an ideal gas does not depend on its pressure, and therefore the enthalpy of reaction with all involved gases in the non-standard state, that means not 1 bar pressure, is the same as the standard enthalpy of reaction. Alright, so if only ideal gases are involved, this enthalpy of any of those gases does not depend on the pressure. Now the Gibbs energy of an ideal gas, however, does depend on the pressure, and therefore the pressure dependence of the molar Gibbs energy of gas A must be considered using this equation. Look at this equation over here. This is the standard Gibbs energy of formation of A. This is non-standard. What's the difference? The difference is RT times the natural logarithm of the actual pressure of A over 1 bar. And why is this? Well, it's simple. dG is negative S dt plus VdP. Alright, if the temperature is held constant, dG is just VdP. For an ideal gas, VdP is just nRT over P dP. Alright, and therefore we can integrate this nRT over P dP. We get nRT times the natural logarithm of P. And now over here, these two are molar Gibbs energy, therefore we remove this n here, it becomes RT times the natural logarithm of pressure. and if the pressure changes from P naught to this P sub A, the Gibbs energy changes by this much. Now let's look at a few examples for this reaction. From H2 and CO2, we get two HCl molecules at room temperature. The enthalpy of formation of H2 and CO2 are both 0 because these two are pure elements, and we have room temperature, and this is the standard state. That means the enthalpy of formation of H2 of 1 bar at room temperature is 0. Same for chlorine. The standard enthalpy of reaction is twice the standard enthalpy of formation of HCl. Why twice? You see this 2 here. Alright? And then we know the standard enthalpy of formation of HCl is negative 92.3 kilojoule per mole. You can look up this value from chapter 00, the appendices. You can find the value from the NIST website, National Institute of Standards and Technology. Alright, and we'll just have this equation. The standard enthalpy of reaction is the products minus reactants. We have 2 HCl as the products, so 2 times this minus reactants, which is 0 and 0. So in the end, we get negative 184.6 kilojoule per mole as the standard enthalpy of reaction over here. So this amount of heat will be released, assuming the isobaric condition. At 25 degrees Celsius, the enthalpy of 1 mole HCl in the standard state is 92.3 kilojoule, lower than the sum of 1/2 mole H2 in the standard state and the enthalpy of 1/2 mole CO2 in the standard state. So this is from this number, okay, 92.3. Now let's look at the same reaction. Let's analyze the Gibbs energy change of the reaction. The standard Gibbs energy of formation of both H2 and CO2 are both 0 again. It's just because, again, H2 and CO2 in the gas phase are chosen to be the 0 references when we define the standard Gibbs energy of formation. Alright, as long as they have 1 bar pressure, room temperature, their standard Gibbs energy of formation are just 0. Now the standard Gibbs energy of this reaction is just twice the standard Gibbs energy of the formation of HCl. We look up this value, it's negative 95.3 kilojoule per mole. Given this number, we can compute the standard Gibbs energy of reaction. Alright, for this reaction, we'll just do the calculation. We get negative 190.6 kilojoule per mole. This is the standard Gibbs energy of reaction for this. At 25 degrees Celsius, the Gibbs energy of 1 mole HCl in the standard state, that means just 1 bar HCl gas, is 95.3 kilojoule lower than the sum of the Gibbs energy of 1/2 mole H2 and 1/2 mole of CO2. This 95.3 comes from here because this is relative to the pure elements such as H2 and CO2. The production of 1 mole HCl gas from H2 gas and CO2 gas may generate electric work of no more than 95.3 kilojoule and 298 Kelvin. Alright, remember this equation. Alright, so if delta G of the system is reduced by this much, we can provide some non-expansion work such as electric work. No more than 95.3 because delta G serves as the lower limit for non-expansion work under constant temperature and pressure condition. Again, the same reaction over here from H2 and CO2 to HCl. We have the standard enthalpy of reaction. We have the standard Gibbs energy of reaction. Again, it's just the products minus reactants. Products minus reactants. You do need to look up the value of the standard enthalpy of formation of HCl and standard Gibbs energy of formation of HCl. Alright? These two are just zeros, these two are just zeros, and then we got those numbers. By the definition of G, we have this Gibbs energy of reaction is the H minus Ts of the reaction. So we have this equation at given temperature, 25 degrees Celsius, and then we can compute the entropy of reaction over here. It's delta H minus delta G over T. Okay, delta H minus delta G over T. We'll plug in the standard enthalpy of reaction and the standard Gibbs energy of reaction here and here, and then divided by temperature in Kelvin, we get 20 joule per mole K. This is the entropy change of the reaction in the standard state. So this is a positive number, so that means at 25 degrees Celsius, the entropy increases. The entropy of 2 mole HCl is greater than the entropy of this H2 and CO2. Alright, so we have this. Assuming the standard entropy of formation of pure elements in the most stable state of aggregation at room temperature are just 0, and then we have just obtained the value of the standard entropy of formation for HCl. It's just this divided by 2. It's just 10 joule per mole Kelvin, because this is the difference between over here. You can see we have 2 HCl, but if you're looking at molar entropy, it's just this number divided by 2. And I want to emphasize this is not the traditional molar entropy of HCl. So we have a traditional definition of molar, standard molar entropy of HCl. This is relative to the oxygen crystal at 0K. Over here, this has a different 0 references. This value is relative to pure elements at room temperature in their most stable state of aggregation. So the standard entropy of formation of HCl is relative to the 1 bar H2 gas, 1 bar CO2 gas at room temperature. Over here, this is relative to the 0K HCl perfect crystal. So these two have different values. Alright. Although we are using different 0 references for this absolute value of molar entropy, and over here for the standard entropy of formation, if your goal is to calculate the entropy change of a reaction, you can use either quantity. You just need to use them consistently. So for example, you can use the standard entropy of formation for all chemicals, and then you can compute the entropy change of the reaction correctly. You can use the absolute values of the molar entropy of all chemicals, and you will get the entropy change of the reaction also correctly, and this too will result in the same entropy of reaction. Again, you just need to use the same set of 0 references consistently for all chemicals in your calculation.